talking about Heimdall. Heimdall is a storage IoT mission controller that we built with an extensive exploration of machine learning pipeline. This work is a joint work between the University of Chicago, MangoBoost, Bandung Institute of Technology, Florida International University, and Argonne National Laboratory. We all use search engine every day. And for example, in this Google search, we have a technology called Hey Google. And however, have you ever been upset when you ask, Hey Google, but then Google answers you in a really long time? And yeah, me too. So the question is, why sometimes it can be fast? It will meet our performance expectation, but sometimes it is slow. The latency is just too big, and the answer came out late. Behind all of these applications that lives inside the Google environment, there is the data center. And inside these data centers, we have all of this traffic from all of the applications mixed in. And eventually, all of this traffic will go to the storage layer inside the data center. And inside the storage layer, SSD is widely used for its performance. Behind the SSD's performance, SSD itself is actually unpredictable due to its internal mechanisms, for example, like garbage collection, buffer flush, and write amplification. When these events happen, all of the IOs that are submitted to the SSD will be delayed. However, these internal mechanisms, since it is internal, it is invisible to the host. Therefore, it is hard to avoid. So what does it mean? So it means when we have a request that we submit to an SSD, when we are lucky, we might get a latency as good as 100 microseconds. But when we are unlucky, unfortunately, we will get a latency as slow as 10 milliseconds. And that's orders of magnitude slower. And when we plot the read latency as a CDF graph, this is what we will see. And we will see a long tail towards the end of the line. And we want to cut this tail latency to achieve this line. So now that we know the importance of latency in our daily life and that Heimdall is a storage IoT mission controller we built specifically for SSDs, you might be asking, what is an IoT mission controller? It doesn't seem very familiar to me. And let me give you an illustration to explain what IoT mission controller really is. So imagine you're in the Disneyland today and you have paid the ticket for one day. And that's why you want to maximize your level of happiness today by riding as many rides as possible and avoid wasting time in the queue as much as possible too. So this is you. In front of you, there are these two rides, the Star Wars and Pirates of Caribbean. Now you ask yourself, to which ride shall I go to elevate my level of happiness faster? And to do that, one thing that you can do is to predict the waiting time. Anybody wants to guess how to predict the waiting time to go to either of these two rides? Okay, nobody. So I think I'll answer it. To predict the waiting time, you can see how many people are lining inside the queue. Because once you are inside the queue, you are trapped there. You waste your time. And the other way to do that is that, so you see the happiness of the people that are going out of their rides. And based on that, you can determine whether you should go to the Star Wars or to the Pirates of Caribbean. And the similar scenario also happens inside the SSD, where if we have these two or more SSDs that store redundant data, and we have an application that will want to read a data from either of these two SSDs, then we can submit this I/O to either of these two. And we want to avoid this I/O for having a large latency due to the garbage collection and stuff's internal mechanisms. So to do that, we employ a machine learning model that can predict whether the condition of this SSD and the resulting I/O latency. So if this SSD is experiencing a garbage collection that will implicate the I/O's latency, and if the model is predicting that this I/O will have a high latency, let's reroute it to the other SSD. And that is what IoT mission controller is. There are a lot of prior works that have been trying to tackle this problem. For example, the random and cloning policies, and also some heuristics like hedging, replica scoring and rate limiting, also forecasting and rate controlling, and finally, the machine learning based. Notably, we call them as LINOS, that is published in OSCI in 2020, and it is improved by Lake in ASPOS 2023 by trying to batch with the GPU inside the kernel. But when we tried this LINOS and Lake on Alibaba, MSR, and Tencent traces, we don't obtain the latency cut and the accuracy that they promised on the paper. So what's wrong? When we read the paper carefully, we saw that they focus so much on the feature engineering and model engineering. Basically, how to frame this I/O admission controller problem as a machine learning problem. What input can we use for the machine learning model, and what output do we expect from the machine learning model? And this study is also including our study to the other ML for storage literatures, which shares the same common problem. They mostly focus on feature and model engineering. So naturally, since the data science pipeline, the machine learning pipeline is actually very long, including the data preparation, data labeling, that we want the data to be really good because we know that garbage in, garbage out. So in order to have a really good machine learning model, we want also a really good data to be fed into the model. And also, since we are applying machine learning for systems or storage specifically in this problem, we want it to meet the latency requirement. And that's why we have to optimize it on the training, of inference, and also in the deployment. So we ask, since the pipeline is long, can we explore the other stages inside the machine learning pipeline to obtain a better machine learning model for I/O admission control? And that is where us, Heimdall, we obtain a superior performance compared to the other I/O admission controllers by extensively exploring all of the other stages. So here's Heimdall. Heimdall is aiming for a tail-free SSDs by shifting this red line of I/O latencies affected by GC closer towards the gray line, in which the I/Os are not affected by the GC, by having two design principles, which is making an accurate prediction with a lightweight and efficient model, so that we will be deployable across many storage systems. By having those design principles in mind, we achieve up to 7 million I/O admissions per second. We achieve up to 10 times more efficient than GPU batching, which is introduced in Lake. We are scoring 15 to 35% lower average I/O latency than the baselines and LINOS. And we are also 4 times faster in terms of inference throughput. But you might be asking, how does Heimdall achieve all of this? Here comes the first technique of Heimdall. Inside the data science pipeline, the first technique is regarding the data, namely the data preparation and data labeling. And then you might be asking, how does prior works label their data? Many of those prior works, as seen in the slides, use a latency cutoff-based methods, in which they have latency threshold to label whether this data is fast or is it slow. This I/O is affected by garbage collection and stuffs, or is it not affected? But the problem with this technique is that if we have a big I/O, then we have to split it into multiple uniform size I/Os. In this case, LINOS and Lake both use page size. And we can already see the problem here. Because we want to use machine learning model to make a prediction for this I/O, then we will end up making too many inference that will implicate the inference overhead and overall the throughput. So that we want to break free from this jail, we want to use variable size I/Os. And when we want to use variable size I/Os, this latency cutoff-based method will produce like mislabeling. Why? Let's see this case where we have big I/O. And when we have this big I/O, the latency will always be big anyway, whether this is submitted to this SSD or rerouted to the other backup SSD. However, with the latency cutoff-based labeling method, this I/O will always be rerouted to the other SSD, which will take a longer time due to the communication latency. And that's why this labeling technique will produce an inaccuracy. we introduce a period-based labeling, a technique that is derived from the insights in the garbage collection. So inside the garbage collection, buffer flush, and write amplification, it will happen for some period of time, and it will implicate all of the IOs that are submitted to the SSD during those time. And that's where we will see a latency spike and a throughput drop. And that's where we call as a slow periods, and vice versa. With this labeling technique, we achieve a more accurate label, and also we can adjust to many workloads. When we already have the labeling technique, we would expect that inside one period, all of the latencies will be stable. All of the IOs inside the slow period will be labeled as slow, and vice versa. However, this is not the case that we see inside the random Alibaba trace, where we see that inside the fast period, there are outliers. There are IOs that is labeled as slow. So that's why we couple this period-based labeling method with a noise filtering algorithm that will filter outliers within the slow period, outliers within the fast period, and short noises. Now that we already have a good data to train the model with, we go forward to the feature engineering and model engineering step. Since these steps are already heavily explored by previous literatures, we ask, can we create a better feature engineering and model engineering? And the answer is yes. I will not go deep into each of this, but there are 4 main features that we derive most important to analyze any IO-based traces, which are the queue length, IO size, latency, and throughput. And with these techniques, we arrive to 11 final features that we show here. Next, we also explore the hyperparameter tunings. I will not go deep also into this, and you can read more in the paper, but now we already have a good model that can make a prediction for every IO to decide whether this IO should be accepted to this SSD or to be rerouted to the other SSD. We already have a good model that can make this prediction. Now we want to deploy this model in the real world production scenario. And when we want to deploy, since these systems have a strict latency requirement, we want to optimize it. And that's where we introduce this deployment technique called joint inference. The joint inference technique derives the inspiration from a traffic light, where it is efficient because we don't have to make a car-by-car decision. We can, all of this car that is lining up can go all at once during the green light. And so we ask, can we make one inference on behalf of multiple IOs? And the answer is yes. And we have a trade-off between accuracy and throughput, but overall, with a joint size of 9, meaning that we make an inference on behalf of 9 IOs at once, we obtain up to 7 million IO admissions per second on a single core CPU. So we break through from the lake innovations that they use patching on GPU, and we use this technique to make an inference on single core CPU, and we achieve superior performance. Now that we already deploy it, we want to evaluate Heimdall. Heimdall is evaluated in these 3 production traces from Alibaba, MSR, and Tencent, and all of them are block IO traces, and we use 500 of them. And we deploy Heimdall across 3 levels, which is the client level with the C++ client that will read the trace and issue a read or write request to the underlying SSD. Also in the application level, where we deploy Heimdall on Ceph, and also inside the Linux kernel, which we deploy Heimdall inside the block IO layer. And we compare Heimdall's latency against baseline random heuristics techniques such as C3, Heron, and AMS. And also the state-of-the-art, which is Linux and Lake. And we also employ hitching on top of Linux. In the kernel evaluation, we deploy Heimdall on Linux block IO layer, in which we compare per percentile latencies and also overall average resulting latency. In the first graph, the right one, we can see that Heimdall, the blue line, is the most stable across all percentiles, and it's even more stable than the other algorithms starting from 99th percentile. And we don't even need hedging on top of Heimdall. which is impressive. So we come to conclusion that Heimdall cuts tail the most. And in the next graph, we show the average latency in which the Heimdall in the blue bar have the lowest average latency. In a summary, Heimdall is a robust IO admission and redirection algorithm for achieving predictability on unpredictable SSTs by having two design principles in which we make an accurate prediction with a lightweight and efficient model so that we are deployable across other storage systems. Since we already showed that Heimdall is deployable across 3 levels, we don't limit Heimdall only on these 3 storage systems. So you can actually deploy Heimdall on other storage systems. And we achieved this superior performance with an accurate labeling algorithm, holistic data science exploration, and joint inference for deployment optimizations. Since we have a time restriction, I cannot explain all of our evaluation results, in which in the paper we also evaluate Heimdall on a large scale scenario and also wide scale, in which we compare Heimdall on various scale factors. We also already open source Heimdall's source code in this link. And since extended machine learning pipeline works for Heimdall's case in the IO admission control, if you have a machine learning for systems or storage project, check out our paper in this QR code. So I believe the extended machine learning pipeline will also work for you, in which we explore more stages, for example, like the deployment and introducing more data labeling algorithm. Thank you, and I'm happy to take any questions.
Great, thank you. Captain Pastor.